Hey, Brandon, can you hear me?
Yep. Yeah, I can hear you.
All right. Are you seeing my screen?
Yes.
Good, thank you. Hello, everybody, all five of you. Thanks for coming. All right, let's get into some solution stoichiometry. So there is some earlier parts to this. I'll get you to read about those. It's about electrolytes and some general things about pHs of solutions. I'd like you just to read about those. I'm going to focus mostly on the math here, the dimensional analysis, because that's really what tends to bother most people about this particular module. All right, let's first of all discuss the difference between gases and liquids. Now, with gases, we have this situation where a gas at STP 22.414 liters will be 1 mole. Now, that's fine for gases, but that does not apply at all to solutions. In solutions, we talk about solution concentration, but it's going to be more about moles of something dissolved in a certain volume of liquid. And 22.414 liters is not something that's going to matter at all here. So what we're going to look at, first of all, is a definition of concentration. And for concentration, concentration is always moles of a solute. No, I shouldn't say that. Let's be a little bit more general about concentration. we'll say an amount of a solute in an amount of solvent or possibly solution. So let's look at the definitions here. If you've got a situation where we've got, let's say, something like this, and let's say we've got like an Alka-Seltzer tablet or something like that. The solvent is what's doing the dissolving. It's usually a liquid, of course. And then you've got the solute. And the solute is what's going to be dissolved in the solvent. Now, after you've added those things together, what you end up with is a solution. So those are the main things I want you to be aware of. That a solute is what's being dissolved. The solvent is what's doing the dissolving. And when you have them together and you've mixed them together and the solute has dissolved, and that's important as well, the solute is actually dissolved, then you have a solution. And the concentration is then expressed as an amount of solute divided by an amount of solvent or solution. It depends on your definition of concentration, what you're finding out here. But there's things like molarity, which is moles per liter of solution, or molality, which is moles per kilogram of solvent. Then you've got percent mass, which is the mass of solute divided by the mass of solution. So there's a lot of times 100%. So there's a lot of different possible ways we can express concentration here. So an example I have on the soft chalk here is a situation where you've got 1 mole of sugar, and then that's about 323 grams or something like that, or 360, something in that region. And then you put that into water and you stir it up, and of course you have a solution that you can look through and it won't have any solid in it. And that would be 1 mole of sugar dissolved in 1 liter of water, and the concentration would be 1 mole per liter. So that would be the definition of molarity. And that's going to be the main concentration unit we will focus on here. So it's going to be mole of solute divided by volume of solution. So whatever this comes out to be. Now, if it's a solid solute, if what's in here is solid, then the solvent volume and the solution volume will essentially be the same. But if the solute is a liquid, then what can happen is the solution volume can be different. And that's not something we're going to worry about too much here in test 2, but we certainly will worry about when we get to test 4. All right, does anybody have any questions?
So it has to be a mixture. It can't be like a compound, basically.
Right. It has to be completely homogeneous, Roland.
Gotcha.
You have to be able to look at it and not see any solid at all. It has to be completely dissolved. Otherwise, you're talking about something different.
And you'd have to separate without doing like chemical reactions and stuff.
Yeah. But we're not doing anything like that. We're just taking a solute, dissolving it in solvent, making a solution. That's it.
Gotcha.
So we're going to be dealing with some relationships here. I've got this flowchart. Flowchart's probably not entirely useful, but the main thing I want to point out with the flowchart is the grand central station is moles. So if you're not starting with moles, if you're starting with mass, you know you're going to get moles. Sorry about there's some noise outside here. Finding it difficult to find a place where I can actually get things working here. So you'll notice I'm in a different location today. I'm actually working from home here, trying to get things sorted out since the office environment doesn't seem to be working out so well for me. It didn't work out for me very well the other day, I can tell you that. Let's take a look at some examples, and let's say we're looking for the molarity. Now, whenever you're looking for molarity, it's always moles per liter. So that's the unit you're always looking for. Often in these kinds of problems, concentration and molarity will be used interchangeably. And that's fine because we're only dealing with molarity as our concentration unit. We're not focusing on any other concentration units here. So it's okay to interchange the two, at least when we're talking about this module. Excuse me. So here is the problem we're dealing with. We've got, what is the molarity of solution of 20.0 grams of sodium hydroxide in 200.0 mils of water? All right, so you can see what the solute is. The solute is sodium hydroxide, and we know that the solvent is water. When we add these two things together, we'll get a solution of sodium hydroxide in water. As you can see, it's a solid clearly here because of the grams, but you know, you can always, I think you should always just make the assumption that we're dealing with solids here. So the solution and the solvent will essentially be the same volume. Let's look at some guidelines here and what I think you should really know in order to be successful with the situations we're dealing with here. So that's our main basis, is the amount of solute divided by, you know, that's just general concentration. But let's focus on molarity and the three equations that are going to be most useful to us. So we know that molarity, which I said is going to be pretty much interchangeable with concentration, at least for this module. Is going to be moles of solute divided by volume of solution in liters. And that way the unit will come out to be moles per liter. We can rearrange this and we can say that the moles of a solute will be the molarity times the volume of solution in liters. And of course, that's going to come out to be, let's just focus, I'll put a box around that. Now the unit here is going to be moles, of course. And the last one here is going to be how we would get volume of something. Now the volume of a solution in liters is going to be the molarity, sorry, the moles of solute divided by the molarity. Okay. So those are the three main equations that we're going to be using here, but you'll notice that they're all based upon the first one. Or the last two are based on the first one we looked at. So we're just rearranging those. All right, does anybody have any questions so far? So what's the point of that? Well, we're starting out, we know that we need to get moles. In this situation, we need to get moles first because we're looking for molarity, which is moles per liter. So we've got to be focused on what we're looking at here. We're looking for moles per liter, but we have grams. So we're going to start out with the grams here. And I want to get to moles. So I'll get grams on the bottom and moles on top. Now I need a relationship between moles and grams. So it'd be 1 mole. And the number of grams would be 40.08. Now what does that represent? Well, it represents the molecular weight. Represents the molecular weight of sodium hydroxide. So you can see that by doing that, we're now at moles. The next thing we need to do is we know we need moles per liter. So we know we're going to have to divide by the volume. Now to divide by the volume, I'm going to do times 1 over 200.0 mils. Now we did something like this last time when we were looking at the stoichiometry. We were dealing with, let's see if I can change this here to something where I'm talking now. I want to see some pictures, but there's too many pictures here. Yeah, I'll try it with this. No. I was having trouble with this the other day, trying to get it to sit where I want to put it. No, still don't like it. All right. And you'll notice that at this point, the grams cancel. We would have moles per milliliter, but that's not what we need. We need moles per liter. So we do a milliliter to liter conversion at the end here. So milliliters will go on top to cancel the milliliters. Liters will go on the bottom, and it'll be 1,000 mils over 1 liter. And that'll give us our answer here, which comes out to be 2.50 moles per liter. Or if you don't want to use moles per liter, you can use big M, but it has to be big M, not little m, big M.
Isn't it the other way?
Isn't what the other way?
The 1,000 milliliters to 1 liter, because because you put it into milliliters and now you want to put it into liters, shouldn't it be 1 over 1,000 milliliters?
No, because I want the liters to end up on the bottom. See, because it's moles per liter. And that's important. You see how the milliliters here will cancel, leaving you with liters down here. Look at all those units, how they've cancelled. It left us with moles on the top and then liters on the bottom.
Well, I guess I sort of look at it as like you're converting grams to moles, and then you're converting those moles to...
Yeah, let me tell you what's confusing you here, and that is the fact that the liters end up on the bottom. So it kind of looks funky because we're not looking for milliliters per se on the top. We need them on the bottom. That's why it has to be arranged the way it is, so that the milliliters cancel to be left with liters on the bottom. What you're saying would be correct if you wanted a unit on top, but that's not what you want.
Okay. So if I wanted to do it, I guess the way that I wanted, like the way I'm suggesting, I would have to do the 200 and convert that into liters, and then I would just do the, I would put the liters to...
Yeah, you would, but I really prefer to do it this way because it does end up giving you what you want for the units at the end. And what's more, it's foolproof. If you arrange it properly, there's no way you can ever get mixed up.
Okay.
And end up having that 1,000 on the bottom, which is a possibility. Sometimes people do that because they have the same kinds of thoughts as what you were having with regard to where those liters have to end up. Yeah, but I'm glad you talked about it because that's a good thing to watch out for.
Well, I appreciate you explaining it.
All right, no worries. Anybody got any questions?
Why do you put 40 grams under the 1 mole? Where do you get that from?
Okay, now the 40.08 grams comes from the molecular weight of the sodium hydroxide. And the thing is, we needed to find a way to get to moles of sodium hydroxide. So 1 mole of sodium hydroxide is 40.08 grams. And I get that, of course, by taking Na, O, and H and getting the masses of that off the periodic table, adding them together. So, but you know, on the quizzes that I give you, I actually give you the molecular weights, so you don't even have to do that.
Okay, that makes sense.
Okay. Does anybody have any other questions? All right. What if we have molarity and we're trying to get to grams? I want to leave these equations up here because I'm going to use them as I go. So this question here is how many grams of sodium hydroxide would be required to make 60.0 mils of a 0.350 molar solution of NaOH. So this is a very common thing that we have to do in the lab. We have to make up things of certain concentrations and we need a certain amount of those things. If you know you're looking for grams, then your grand central station should be moles. So you know that you'll be starting with grams, but you know that the first thing you'll want to do is get to moles. And once we get to moles, then we can, we need grams. So, but we know that to get to grams, we'll need moles to get to grams. So let's have a look at how we might do that then. So I've got the volume here, I've got the molarity, and I've got this equation here that will give us the moles. And this is what I was talking about. We need a way to get to these moles. And we can do that by taking the molarity and multiplying it by the volume solution in liters. That's according to this equation that I'm showing you right here. Can you all see my cursor here? It looks like a little pen. Can you all see that? Yes or no?
Yes.
Okay,
Yes.
good. Thank you. Sometimes I have a cursor and it actually won't show up on Zoom for some reason. I can see it, but you guys can't. But it looks like this one's possible to see, which is good. So we're starting out, we need the molarity. Now you can start with the molarity or you can start with the volume here because we're multiplying them together. Just for kicks, I'll start with the molarity. So it'll be 0.350. And I'm going to make it moles per liter so that I could more easily see the units. I'm going to multiply it by this volume, 60.0 mils. And the reason I'm doing that is because I know that to get moles, I'm going to have to multiply the molarity by the volume. Unfortunately, it's not in liters. So now I'm going to have to do a conversion. Now, so somebody had asked earlier, I'm not sure who it was, but somebody had asked earlier about the liters to milliliters conversion. And you'll see this one's going to be a little different. So the milliliters will go on the bottom here to cancel, and the liters will go on top. So we'll have 1 liter on top, and then 1,000 on the, and 1,000 milliliters on the bottom. Does anybody have any questions? So if I do that, you can see that the milliliters cancel, and now the liters cancel as well. See, they don't have to be right next to each other to cancel. And at the present time, what I'd be left with is moles, but that's not what I'm looking for. I'm looking for grams. So you can see that's what I had to do first, was get those moles. So now to get those grams, I know that grams will be on top and moles will be on the bottom. And the relationship there is 1 mole will be on the bottom and 40.08 grams will be on top. Again, that's the molecular weight of sodium hydroxide. Sorry about that. We have the grams over here. And when we do the math on that, it comes out to be 0.842 grams. So what does that represent? Well, if you had 60 milliliters of solution, 60 milliliters of water, I should say, and then you put in 0.842 grams of sodium hydroxide, you'd end up getting a solution that has the 0.350 molarity that you were looking for. All right, does anybody have any questions? So now in this case, we're looking for volume of water. And we're given a molarity and we're given a mass here. Now, if we're looking at the solutions, the formulas up here for volume, we've got volume of solution is going to be moles of solute divided by molarity. Now we have grams. So grams needs to be converted to moles, and I'm going to divide it by molarity. So let's see how that works. So I'm going to start out with the 10.0 grams here. And now I'm going to try and get to moles. So moles will be on top, and grams will be on the bottom. So 1 mole, 40.08 grams. And we're trying to get to, again, volume. And we know that to do that, it's going to have to be moles, which is where we would be at now, divided by molarity. To get this, I use 1 over the molarity, or the flip of it, which would be 1 liter, divided by 0.560 moles. Now, this is something that a lot of people struggle with, is why I flip this over. But the thing is, to divide by something is the same as multiplying by its flip or its inverse. An example would be if you were going to divide by 2, that's the same as multiplying by 1 over 2. So it really is the same thing. But the reason we're doing that is so that the units can cancel to give us what we need at the end. So by multiplying by the flip of the molarity, you're essentially dividing by the molarity, which is what the formula here requires if you want to get to a volume in liters. Does anybody have any questions? Now, I haven't specified in the question what unit I want for the volume, but if I wanted just liters, I could just leave it at that. If I wanted to go to milliliters, which I will do just for kicks, then I'll put liters on the bottom, I'll put milliliters on top, and that'll be 1,000 mils, and then 1 liter. And then that will give us our final answer, which comes out to be 446 mils if we wanted to go that far. Oh, by the way, with significant figures, generally just look at the beginning figure, the one you start with. That will generally give you. But sometimes, you can also look at the molarities as well. That could be helpful in order to figure out how many significant figures you need at the end. Does anybody have any questions? Usually people have questions about that one because, that's kind of annoying to have to flip over that molarity to divide by the molarity. Now, I mentioned mass percent before as another means of expressing concentration. But let's say you had something like, what is the mass percent of solution made by mixing 34.5 grams of NaI into 100.0 grams of water? So if you've got a mass percent, I'll just do it in general terms here first. A mass percent is going to be the grams of solute divided by the grams of solution. Remembering that's times 100%. Remembering, of course, that the grams of solution is going to be grams of solute plus the grams of solvent. So that's important. It's important to make that distinction between what I mean by grams of solution and grams of solvent, because the solution includes both. So you can see that the work for this one, if I wanted to figure out the mass percent in this instance, is going to be 34.5 grams. Now this is for the sodium iodide, or NaI, but that will be over 34.5 grams plus the 100.0 grams of water. The biggest mistake I see people make here is they'll just use the 100.0 grams of water, but that would just be the solvent. It needs to be the solution. But think about what a percentage is. If you've got a percentage, it's always part divided by whole, right? Part divided by whole. And when we're talking about whole, the whole has to be the whole thing, which would be the solution. If I wanted to figure out the percentage of females on this call, I would add up the number of females and then I would divide it by the number of people on the call, everybody. That's the whole. So it'd be females divided by males plus females multiplied by 100%. This is nothing different from doing that, really. There is a bit of a significant figure wrinkle that you have to be aware of here because we are mixing operations. So we have to do the addition first here. And that will end up helping us to find the significant figures at the end. So 34.5 grams divided by here, 134.5 grams. Because that's going to go by number of places past the decimal point. And this ends up being 3 significant figures at the end. So that's going to end up giving us our final answer, which is going to be, well, I don't know, let's have a look up. Sorry, 25.7%. Sorry, just trying to enlarge this a bit. There we go. So 25.7% would be the final answer there. All right, anybody got any questions about mass percent? So the next thing we're going to look at will extend what we've already talked about into the realm of what we talked about on Wednesday. Sorry, was it Monday? And that was stoichiometry. So now we can actually apply this to chemical reactions that involve solutions where we have two things of different concentrations or two things of different concentrations, different volumes or masses in order to figure out a mass, a volume, or another concentration of something else. So that's what we're going to be focusing on. I am using this flow chart here, but I'm going to, again, go back to the flow chart that I was using on Monday, and that is just this more simplified flow chart where we start off with a quantity of something and then we convert it into moles. So Q of A goes to moles of A. This goes to moles of B. And this goes to some quantity of B. Now the quantities we're dealing with here are a little different than what we were dealing with the other day because we are dealing with solutions. So we are dealing with grams. We could also deal with volume in liters. And we can also deal with concentration, which is of course in moles per liter. And we can also find those same things for something else. So that's going to be the basis of what we're going to be using in order to get to places. But you can see that in the actual flow chart, the main thing that we're looking for is this moles of A and moles of B, because it's in the center here. So we're always looking for moles first. So often you'll see this situation playing out, molarity times volume of solution in order to get to moles. That's going to be very common. But the volume of solution is going to have to end up being in liters. So you'll be doing a lot of conversions on the fly here in order to get to where you need to get. But the main thing I want you to try and focus on is the big picture here of what we're doing, starting out with a quantity of something and then going to a quantity of something else. And because we're dealing with two different things here reacting, it's going to be important for us to make sure that we include not just the units, but the units and the compounds as well. So let's look at some examples of those kinds of situations. What is the volume of 0.532 molar HCl, molarity HCl, that will react with 10.0 mils of 0.430 Na2CO3, molar Na2CO3? You'll notice in this kind of question, you're always given a reaction. You always will be, and the reaction will always be balanced. We need this in order to get the mole ratios so that we can do something intelligent with our conversion through this process. Now, the question, of course, is going to be, well, where do you start? There's a lot of things with numbers here, and you're just trying to sort out what you're starting with would be the first thing that I would look for. Now, there's a couple of things that you can do, a couple of clues that allow you to tell where to start. I think one of the easiest things is to look at the verbiage and say, well, what volume of? And you can see where we're looking for HCl. So we know we can't start with what we're looking for. So that would be my go-to there, is not to start with HCl, but to start with the Na2CO3, because the HCl is what we're looking for. And I know that because of what the question is being asked about. Another clue is often how much information we're given about each thing. And generally speaking, we're going to be starting with the thing about which we have the most information. And when you look at Na2CO3 here, you can see that it has two bits of information associated with it. You've got a volume and you've got a molarity. But on the other side here, we've only got one thing for the HCl, and that's the molarity. Does anybody have any questions? Does anybody have any questions? All right, so let's see how we start this. Now, as I said, I telegraphed this earlier, and because we've got moles in the center, we know that the first thing we're going to be looking for is moles, and it's going to be very common for us to have a situation where we have a volume and a concentration. Now, whether we start with the volume or the concentration is immaterial because we're multiplying them, so it's going to be the same thing. I'm going to start with the concentration. I generally do, but I don't have to. But what I usually do is take the big M and convert it into moles per liter to make my units a little bit more, make a bit more sense. So I multiply that by the volume, recognizing I have milliliters, but I really want to get that into liters. So liters will be on top and then milliliters will be on the bottom. So it'd be 1 liter and 1000 mils. Does anybody have any questions so far? Now I'm going to have to put the moles of, I did forget to put this in, moles of Na2CO3. Otherwise, the next part won't make any sense. Now at this point, that's what I have is moles of Na2CO3. I would be right here. That's where I'm at right now. But I need to get to moles of HCl. So I know that moles of HCl will be on top. And the moles of Na2CO3 will be on the bottom. Now, the reason I'm doing that is because I know I need moles of HCl. That's going to be the next step. And the moles of Na2CO3 will end up cancelling. But what's the relationship between these two? Well, we get that from the reaction, and you can see it's going to be 2 moles of HCl for every 1 mole of Na2CO3. And at this point, this is where we're at. We're at moles of B, which is moles of HCl. I'm going to stop here for a second. Does anybody have any questions?
So you're trying to find the molarity of each of the solutions. What are you doing exactly?
Well, I'm looking for a volume of HCl. And what I'm trying to do here is I'm starting with a volume and a molarity of Na2CO3. I'm using the reaction here as well. But David, the main focus is on this flowchart. The quantity of A here is essentially a concentration and a volume, these two things, in order to get to moles. But then I have to get to moles of the other thing as well. And I do that by using the reaction. I'm not done yet because what I need is a volume of HCl, which I haven't found yet. Right, I'm not done with the problem. I'm just stopping here to make sure that people understand what I'm doing.
Okay. All right.
So the next thing I need to do is I need a volume of HCl. Now, to get a volume, it's moles of something divided by the molarity. So this is when I use that flip again. I'm going to have to work my way down here. Oops. And we're going to multiply by the flip of the molarity here. So that would be 1 liter over 0.532 moles of HCl. And if I wanted it in milliliters, then I'd do one more conversion. Put milliliters on top, liters on the bottom, 1 liter, and then 1,000 mils. And that will give me my final answer, which comes out to be 16.2 milliliters of HCl. Sorry, it all got a bit squashed up in there at the end. See, these end up being kind of longish transitions once you put this all into the flow chart here. But we're using the same skeleton as what we were using for the module 9. So David, I don't know, is there anything I can tell you that would make this a bit easier for you?
Nah, it's fine. It's just a little bit confusing.
Well, yeah, I mean it is, but you know that's why I try and preach about doing it one step at a time. Yeah, always looking for what you need at each point. So starting out with a quantity, going to moles, then going to moles of something else, and then quantity of what you want at the end. Sort of make it a 3-step process. Don't try and think of it as just one big long equation, because if you just look at the one equation, it's not going to make any sense to you. That's why it's important to break it down and understand what you're looking for at each point.
Right. And this is all this is all well explained in the soft chalk also. So
It is, but you know, that's the whole point of what I'm trying to do here is really just trying to get you to break it down into the steps that appear in this flow chart here. If you do that, I don't really feel like there's any way that you can go too far wrong with it.
right, okay.
Okay, let's look at another example here. I'm going to try and stretch this out a bit here so that I can have a bit more room to work with. So we're looking for the mass of sodium hydroxide, or NaOH, that will react with 150.0 mils of 0.600 molar H3PO4. So we know that we can't start with the NaOH. We have to start with the thing that we actually have information about, and that's the H3PO4. Now, given that we have both a volume and a concentration, then again, we're looking at this situation where we can find moles. All right, so we've got our volume and the concentration. I'll go ahead and start with the concentration. So 0.600 moles per liter times the volume, 150.0 mils. Now this will allow us to get to moles if I do a conversion here. So liters will be on top, milliliters will be on the bottom. And it'll be 1 liter and 1,000 mils. Now at this point, that's moles of H3PO4. I keep on forgetting to add in the actual compound here. It's important. Moles of H3PO4. This is where we're at now, because you can see that the liters cancel, the milliliters cancel, and we're left with moles of H3PO4, which means we're at this point in the flowchart at moles of H3PO4. We're looking for next moles of NaOH. So moles of NaOH will go on top. And that'll be moles of H3PO4 on the bottom to cancel the moles of H3PO4 we have on top. The mole ratio is 1 mole of H3PO4 and 3 moles of sodium hydroxide. I'm getting that from the equation. If I stopped here at this point, I would be at moles of NaOH because the moles of H3PO4 would cancel. All right, so moving down here, we need, what are we looking for? The mass. So we need grams of NaOH on top and moles of NaOH will be on the bottom to cancel with what we already have found. And the relationship there is 40.08 grams of NaOH to 1 mole of NaOH. And that answer came out to be 10.8 grams of NaOH. So again, it's just stepping through the flow chart here. We start out with our quantities, and it's always moles that we're looking for first. So generally you'll have a molarity, you'll have a volume, you multiply them together. You'll do a conversion on the fly to get the milliliters into liters, and then everything cancels and you would have moles at this point, moles of H3PO4. The next thing you want to do is find the moles of NaOH, and that's where the reaction comes into play. and then you figure out what you need at the end, whether it be a mass, a volume, or a concentration. In this case, we're looking for a mass. And that's how we would get to the end of this one with NaOH. Does anybody have any questions? I feel like we've already done one like 8, so I'll see if we can. Let's look at the titration questions. Now, titration, we're generally looking for a concentration at the end. So we've done a problem where we've got a volume at the end. Now we've done a problem where we've got a mass at the end. This one allows us to determine the concentration of something at the end. And during titrations, we do a lot of this. And I think, well, at some point, when you're doing titrations in lab, I know you're doing one pretty soon. Are you doing one already? You doing titrations yet?
I don't think we have done titrations yet. I'm pretty
No,
sure
not
it's
yet.
coming
Not yet.
either
Okay. I think
this
maybe
week
next.
or next.
Yeah, this week or next, I think you'll be doing it. Okay.
This week I'm doing it, or at least I'm watching a video of you doing it.
Oh,
so.
yes. It's just like being there, Chloe. Just like being there.
Especially when it
funny.
keeps going in and out of focus, it's like peak cinema right there.
Well.
Yeah, it was funny because like when I was taking pre-chem and everything like that, or intro to chem, it was just like seeing all these videos like, who is this man?
Well.
Based on name.
We get a first-hand experience with the man behind the camera.
Yeah, for what it's worth. All right. All right, so let's look what happens when we're looking for a molarity of something. And this is where we have, in this case, a volume. So it's a sample of 25.00 mils of HCl with unknown molarity is titrated with 35.56 mils of 0.502 molar sodium hydroxide. So in these titration problems, you're always starting with a volume and concentration of something, and you're looking for a molarity of something. And to get that molarity, you are going to use a volume. Now think about what a titration looks like. Right, you'll have something in a burette and then something in a flask. And generally speaking, you'll know the molarity of what's in the flask. So you'll know that. So the molarity of, and I'll put X in here. So molarity of X, yeah, you'll have an idea of that. And in this burette, it's not a very good picture of a burette, but you know what a burette looks like. We have some solution Y that molarity, we don't know. But what we do know is the volume of Y that gets added. So we know the molarity of X. We also know the volume of X as well. And we don't know the molarity of Y, but we do know how much Y was added to X through the burette. And that's the whole point of a titration. That's what you're always doing. So all of these questions are going to be similarly set up with a molarity and a volume of something that you know, but you assume is in a flask. And then a volume of something you don't know the molarity of that's in a burette. And what you're interested in here is that molarity. And that's the whole point of a titration, is finding a concentration of something you don't know the concentration of. Does anybody have any questions so far? All right, so with that context, it makes it a little bit easier to understand the setup of what we're doing, especially when you look at the wording of the question. It says, what is the molarity of the HCl solution? We know we're looking for the concentration of HCl, which means we can't be starting with the HCl. We have to start with the NaOH, of which we have a volume and a concentration. And to get to moles, we know we're going to have to multiply those things together. Oh, I did. Looks like I got rid of my, let me see if I can get that back. No, I can't. All right. I accidentally removed my flowchart here. So I'll rewrite that. So we're still using this same flowchart because in titration reactions, we still have to do a mole-mole ratio as we go. So let's look at what we're starting with here. We're starting with, again, the concentration, which I usually do convert to moles. This time I'll remember to put the compound in here, moles of NaOH per liter. Now I'll multiply that by the volume that we're given. And then we do our conversion here in order to get to moles. So the liters will be on top, the milliliters will be on the bottom, 1 liter, 1,000 mils. So by doing all of that, we have moles of sodium hydroxide, which is what we want first. So we're at this point here right now. Now we need to get to moles of HCl. So moles of HCl will be on top. And the moles of NaOH will be on the bottom. Now the mole ratio is going to be given by the actual reaction. It's going to be 1-to-1 in this case. It's not always going to be 1-to-1, but it is 1-to-1 in this case. And then that would put us at this point, moles of HCl. But what we're looking for here is a concentration. Now to get to a concentration, according to the equations I have up here, I'll have a mole of solute divided by a volume of solution in liters. So what I do is I do times 1 over the volume given, which is 25.00 mils. Now, why am I doing times 1 over? Because I need to divide by that volume. But that needs to be converted into liters. So milliliters goes on top, liters goes on the bottom, 1,000 mils and 1 liter. And that comes out to be 0.714 moles per liter. And of course, this is going to be HCl. So that gives us our last step there to get to our concentration of HCl at the end there. All right, anybody got any questions? Yeah, it is like my psychiatrist told me. I told my psychiatrist I was afraid of stairs. You know what he said to me? He said, take it 1 step at a time. That's what you should do here too. You know, you've got your flow chart. You know what you need to get at each step. And if you take it that way, figuring out first of all the moles of what you have, then figuring out the moles of the other thing using the reaction, and then getting either the mass, the concentration, or the volume at the end, then you'll be okay. All right, anybody got any questions? Now we can start with some other things here as well. Let's see, what's this one? This one's very similar. I'm not going to do that one. All right, no, it's the same thing. Okay. All right, I think I will do that one, since that is the last problem. It's really a repeat, though, of this one. So what are we starting with? We've got the sample of 20.00 mils of H2SO4 is titrated with 26.78 milliliters of 2.50 milliliters of solution to an endpoint. What's the molarity of the H2SO4 solution? So again, we're starting out here with the sodium hydroxide because that's what we have all the information about, and we're looking for H2SO4. So again, you're seeing these same patterns playing out. So 2.50 moles per liter times the volume given, 26.78 mils. And then a conversion in order to get that into liters so that they cancel out. We end up with just moles. And again, I forgot to put my compound here, so we're starting with moles of NaOH. The next, so at this point, this is where we would be. We would be at moles of NaOH. The next place we want to go is moles of H2SO4. We know that those moles of NaOH will cancel. So it'd be 2 moles of NaOH to 1 mole of H2SO4, and we get that from the reaction. You can see it's 2 to 1 here. At this point, we would be at moles of H2SO4 in the flowchart. The next thing we need, again, is the molarity, and we do that by times 1 over the volume given, which is 20.00 mils. And that's for the H2SO4. And then milliliters will be on top, liters will be on the bottom, and we will end up getting moles per liter. See, the milliliters cancel. The moles here cancel, milliliters, liters cancel, and the moles of NaOH will cancel as well. So all we're left with is moles of H2SO4 and liters, moles over liters, which is what we want as our unit at the end. And that came out to be, in this case, 1.67 molar. Moles per liter. All right, does anybody have any questions? Is that a question I'm hearing or not?
When I'm looking at this question, it looks like there's much more steps in the 3 steps of the flow chart. Like how does that work? Like could you link each step that you did in this equation to a step of the flow chart for me so I can visualize it?
Okay. All right, so let's do this part here. So this business here that I'm putting under the bracket, this gets us to mole of A. So we're taking a concentration, multiplying by a volume and converting that volume into liters. By doing all of that, we end up getting moles of sodium hydroxide. This next part that I'm putting under the bracket here gets us to moles of B, which is moles of H2SO4, and that's where we use the reaction. This last part, where we divide by the volume, whoops, I didn't put in my numbers here, where we divide by the volume and convert into liters, is how we're getting to the last thing that we need, which is the quantity of B, which happens to be a concentration in this case.
Okay.
So, I mean, look at the first part I've got under the moles of A, David. You know, it's all based on what I've got up here: molarity times volume of solution in liters. But the volume of solution is given in mils, so that's why I convert it to liters to satisfy what I have here. So did you see what I'm doing?
Yeah, no, I get it.
Okay. And this is why I try and focus on splitting it up into those 3 steps: moles of one, moles of the other, and then the quantity of what you want at the end, using these equations here, these molarity equations, as your basis, depending on what you want at the end. You'll always know what you want because the problem tells you. You want a volume, you want a concentration, you want a mass. It will always give you what you want at the end. Is there anything else I can help you with on that?
No, not really. Thanks for explaining that.
Okay. Let's take a look at the we'll look at the assignment here. So the assignment, again, it's this matching thing. And be careful, especially with unused answers, making sure that if something's unused, you do put the number for the unused answer and the one you didn't use. It's not a bad exercise. It certainly allows you to figure out what you're doing and making sure that you understand. It's a bit of a bear. People don't like it because it's a bit time consuming. But still, if you know what you're doing, it shouldn't take you that long, maybe 30 minutes. If you don't know what you're doing, then, well, it gives you an opportunity to figure it out.
So is the only reason the unused answer option is there is just to like see if it can trip us up or something? Like I never really got the point of it being there.
It's so that I can throw in red herrings. That's exactly right, Chloe.
Okay, yeah, that's what I figured, but I always was just like, oh, so because sometimes, like, when it's literally only like 3 answer choices, it's like, okay, I guess this is here now.
Right. So, well, just to this is a good example, this one here that I'm showing you here. So we want grams at the end. Sometimes you don't even have to do it in order. If you know you want grams at the end, you know that grams is going to have to be number 4. So the only thing that has grams is the molecular weight here. So that we know is number 4. We also know that moles is going to be part of this, and we'll have moles at this point once we've done the first part of the equation. And to get to moles, then we've got the problem here, are required to make up a 15.0 mil solution of 0.250 molar. So we know that we're going to multiply those two things. We've got the 0.250 molar here. So the number 1 must be this volume, this 15.0 mils. So that'd be number 1. Now 2/3 will be the conversion, making sure we have liters on the bottom. So 1 liter will go in number 3. And in number 2, we'll have the moles, 1 mole here. And then the 5 would have to be the 1 mole. Hang on, let me see. What have we got? No, not 1 mole up here. Number 2 is 1 liter. sorry, it's 1 liter, 1,000. Now I've confused myself here. Sorry about that. Now that's the liter conversion. So it's 1 liter, 1,000 mils. It goes on the bottom here. Sorry about that. And the moles will go on the bottom here. So 5 would be 1 mole. And where did I put my 2? My 2 is 1 liter. There we go. Okay. And the point I was trying to get at here is that the rest of these would be unused. So you would have the 1 here, which is commonly used when finding a volume because it'd be 1 times 1 over something. And the molarity here is not of any consequence either. So yeah, it is just there to see. It even confused me as I was doing it, Chloe. So I'd have to know what I was doing as well when I'm doing this to make sure. But one of the things I can tell you that really helps is actually writing it out rather than trying to do it in your head, because that's where I was just getting tripped up just now. Was trying
Yeah,
to
that's
do it
the
in
way
my
I
head.
normally do it. I
Yeah.
usually, yeah, I was like, okay, he's gonna just do it in his head. I mean, I guess he's the teacher. But
Well, yeah, but you're right. Generally speaking, it's better to write it out and make sure you understand where the things are going.
But yeah, like what you were saying, like as first you started, like you see like the 4s there, and you know that has to be grams. That's I usually like try to like put in like the placeholders as soon as I can, and then I just like write it out and fill out the rest. That's how I usually do it. So
I think that's a really good idea. Making sure all the units cancel. The other technique I like to use is not putting in any numbers until the end, just putting in all the units first, making sure they all cancel, and then looking for the equality relationships between those to put the numbers in. And generally that gets me to where I want to be.
yeah, that makes sense actually. Yeah, I might actually try that sometime because it sounds like a really good idea. Like if it's like a really long problem or something like that, like it'd be good to just get everything in place and then fill it out. Yeah.
All right. Let's see the other things you'll be doing. Do the practice quiz here. And that's where you'll write the things in. And you can get an idea of the formatting. I would strongly recommend for this one, not doing this initially. I would just go down to the end and submit it so you can get an idea of the format that I'm looking for each of these, and then you won't get too confused later. So that just gives you an idea of the formatting, and you say, oh, okay, that's what he wants. All right. You'll notice here we've got milliliters of A, liters of A, all of that. So you can avoid some hassles for yourself down the track if you simply just submit it and look at the formatting that it's being looked for, and then you won't get all that frustration of going through doing it and saying, oh, I didn't get 80% because I didn't get the formatting right. All right. Does anybody have any other questions that they want to ask about this?
I have an unrelated question to that specific module, but it's about, I think it's called the empirical formula, where you try to figure out the number of each in comparison, like 1 to 2 or 2 to 1.
Right.
I'm pretty confused as to how to reach that end. Like very frequently I'll get the correct amount of moles for each of the ionic compounds, but then I can't really figure out how to actually get the empirical formula. Could you show that?
Oh, well, I'll talk to you after class about it, David. So just hang around.
Okay, sure.
Just hang around. If anybody else wants to hang around and see me answer that question, you're more than welcome to do so. But for everybody else, I'll see you all on Monday.
Thank you.
All right. See you later.
Thank you.
All right. Who we got left? Kaylee, you going to hang around? Kaylee might not be here. Okay.
I'm here. Sorry, my phone, my computer.
No, it's okay, Kaylee. It's all right. You're going to hang around?
Yes, I'm going to hang around for a little bit.
Okay.
I just want to watch.
Okay, that's good. That's good. All right. So, David, do you have a specific problem you want to talk about?
Not necessarily. I was just doing my lab homework the other day, and I realized that I had no clue how to reach the end goal correctly. I thought it was just dividing the smaller number by like the bigger number, and you would end up with.
There's a little bit more to that. It's just
Okay.
that one part at the end. Let's look at the assignment here. Well, maybe not the assignment. And let's not do that. Let's look at the. We'll do the practice quiz here. Okay, I'm actually going to submit this because I want to see if there's a problem here that will be a good one for you to look at. There we go. All right, let's look at number 7 here. Okay. The 25.9% and 74.1% O. I'm going to stop recording right now.